In this video, we're going to be going through transfer learning. So transfer learning is about taking a pre-built a deep network, and then we're going to be reusing those weights in another different problem. Okay, so in this case, what we're doing is we're going to be looking at this neural network called VGG16, and we're going to be reusing the weights to classify between dogs and cats, hence the Doge meme over here. Okay, so I really hope we are running the Docker container, by the way, which is shown in the deepschool.io installation instructions. So yeah, anyway, let's move on. So the first few blocks is really not relevant to the actual deep learning in itself, so I'm just going to run through them. So the third block is downloading the relevant data. Okay, and I'll talk about these bottleneck features in later on in the tutorial. Let's jump. Oh, and fourth one. So what it's doing over here is there are some corrupted files in this folder. So in the pet images folder, there's some files that's 0 size in length. So we're deleting those things. Now, unfortunately, the way that Keras is structured when it comes to training on images, it needs to be in particular folders, right? So in whatever the data set is, you need to separate it out in train and validation sets, and even within the train set, you need to specify what the folder it is in, right? So whatever class it is, you have to specify that. So all the dog images have to be in the dogs folder, or the cat images have to be in the cats folder. You don't have to name it cats; it just needs to be in a separate folder. Okay, so same in the validation or test set. All right, so what we're going to be doing over here is we're going to be choosing it's approximately 25,000 images. We're going to choose 20,000 as training set, and then we're going to separate. We're going to put them into separate train and test sets. Because keep in mind, all that there is in the actual data set is just dogs and cats, and it's not separated in train and test. Okay, so we're np.random.permutation is going to randomly permute all those 25,000 images. Okay, so just to show you what that function does, let me just quickly just show you. If I go random.permutation 5, it'll show you, so there'll be a number between 0 to 4 randomly arranged, right? So that's what it's doing. Yeah, oops. So it's going to be choosing 20,000 over there. Okay, so keep in mind the labels have to be in the same order, right? So that's why I saved this permutation thing and then choosing 20,000 and the 20,000 over here, and the rest as test labels. Okay, and the rest of it is what it's doing is it's going to copy those into a train folder and a test folder. Okay, so each time it runs, it's going to create a separate set, and that's why I want to remove the existing train folder and create this thing. So let's just move on, because this is important to deep learning in itself. So let's just skip ahead. Okay, so now we're going to get started in the deep learning side of things. So one thing with images that you can do is, if you shift the image by a few pixels here and there, the content of the image is still the same, right? So it isn't. So if we have a dog image and if you shift it to the right a bit, it's still a dog image. So this rescale thing over here is rescaling all the pixels so that it lies between 0 and 1. Okay, so because keep in mind that an RGB image, that all the values of the pixel is going to be between 0 and 255. You divide by that 255. The zoom range over here, so this was a bit confusing, but what it's saying is that you can zoom into the picture so that it's 0.8 of what the image was and 1.2. Okay, so it's actually 1 minus 0.2 and 1 plus 0.2 is what it's looking at. And horizontal flip means the contents of the image will be exactly the same. Well, the label of the image will be exactly the same, even if you flip it horizontally. So vertically, not so much, but it depends on the domain, right? Okay, and I want the image height and width to be 100. All right, so going ahead, I just want to show you some of the pictures that it gets. So there's two things that you need to remember in Keras. So there's a data gen thing. So you call the image data generator class, and you create this data gen object. And then from the data gen, I'm going to start flowing from the train folder directory. Okay, so again, I create this data.gen object, which says this is how I'm going to play around with the image, and then I'm going to start getting that data from this specific directory. In this case, it's train folder. You had to specify the color mode, which can be RGB or grayscale. And yeah, so the batch size is 1 for this thing. And for now, I'm going to say class mode is none. Okay, so later on, we'll have to say it's binary. But I just want to show you what the images look like. Okay, so just to show you the images, yeah, so over here, so from the train generator, so keep in mind this is the generator that it's making. I can get yeah, so I can get 5 images, which is what I've done, and I'm showing it to you over here. Okay, so that's what it looks like. So we have a few dog and cats in there. Okay, now before any machine learning or deep learning thing, you have to use a basic machine learning algorithm, and in this case, it's logistic multi-class classification. Okay, so now I'm using sklearn for this. So just ignore this for now. All I'm using this one is to get 1,000 images. Okay, as the training and my testing. Yeah, but what am I doing here? Okay, so I'm using logistics from scikit-learn. I'm importing logistic regression, and then I'm going to fit it. Now, the reason I only use 1,000 is because scikit-learn can't generally deal with big data, right? So that's why I'm only using 1,000 classes. But again, when I'm fitting it, just notice how I reshape my data set. So the X train is going to be 1,000 by 100 by 100 by 3, or is it 1,000 by 3 by 100 by 100? Anyway, it's because it's RGB, it's that we will have a 100 by 100 by 3 component, right? So I really don't want that. So I want to flatten it. So that's why I want to reshape it by batch size, and -1 means whatever the rest are, it's just going to ignore it. Okay, so it's just going to flatten the rest of it. And I've given it the Y train, and then I predict it. So when I go logistic.predict, it gives me the classes, and if I go predict probability, proba, it will give you the probabilities. Anyway, so the accuracy of the test set in this case is 51%. So it's really like just tiny bit better than random. And I'm pretty sure this 1% is random on itself, so I would completely ignore the results of logistic regression. So the point is, it is a hard problem as far as the conventional ways are concerned. So let's try something a bit more advanced. So from my previous tutorial, you can go ahead and check the video. I did convolutional networks. So in this one, I'm building a convolutional network, and it just generally goes convolution, activation, and max pool. Okay, so the first kernel size is 3 by 3, and I have 8 of them. And then go 8, 16, 32, and so on. Now, keep in mind, I'm also using batch normalization from the second set onwards, right? So the first set, keep in mind, you don't use batch normalization in the first bit. You can go back to my previous video to check on batch normalization. So I'm going to skip out on explaining that too much. But in general, we just have the convolution, activation, max pool, and we have 3 of those. 3 or 4. Yeah, 4 of those. We flatten it. Keep in mind, you have to flatten it before you pass it on to a dense layer. So, and the dense layer is a sigmoid. A sigmoid because we want a binary classification, right? Okay, so let's see how this ends up. So just to show you the number of parameters, I have 16,000 parameters, but only 15,000 trainable. The rest are from the batch normalization part. Okay, so that's 160 parameters that's coming from batch normalization part. Okay, so when I fit it, and oh, by the way, just notice how I put metrics is accuracy, and this has to be sent in as an array. Okay, so you can't just say metrics equals accuracy for some odd reason. Yeah, so the accuracy goes in the train set on itself. It goes from 63 to 69%. So you'd think we're doing slightly better, but when I go and look at the test set, it's not actually doing that much better. It's at 50%. Now, to be completely fair, I didn't really give it that much time, right? So I am training on a CPU, and like it's like what is this, like 6 minutes or something. So yeah, so if I had trained it for a bit longer on a maybe even on a GPU, so say like 10 minutes on a GPU, I think I would be doing far better than this. Like, so if you go to the Keras blog, which I've referenced right at the top, right there, right? So it says, I think it gets up to like 80% accuracy using a GPU. Anyway, so let's move on. So this lesson is about transfer learning. So now we get on to the transfer learning part after the convolutional set. So I'll let you read this part by itself, but the point by just a plain convolutional network, it likes to classify everything as a dog, because dogs are better, of course. Okay, so transfer learning. So with transfer learning, I said we're using the VGG16 network. Okay, so just to show you what the network looks like, it looks like this. There's a whole bunch of layers, right? And there's I think 15, like this is a truncated version of it. So that's around 15 million parameters. So it's a huge network. But the key thing, there's two things. So in this one, I'm going to say with the data generator, it's only going to rescale it to be between 0 and 1. Okay, so no fancy stuff like rotations or any of the other options that you can have. But the key thing, the really big thing, is that I'm saying include top equals false. So what include top equals false is doing is it's removing all the dense layers from VGG16. Okay, so if it has 3 dense layers, it's going to remove that, and that's just a Keras default. It's not that it's saying go and find the dense layers and remove it. It's generally what you do when you do transfer learning. You take out the top few layers. So yeah, so it says include top equals false, and you have to give it a input shape. Okay, so in this case, it's 100 by 100 by 3. Right. So I think there were different versions of VGG16, so that's why the weights equals ImageNet thing you had to specify. Yeah, so I think I've done that twice for some odd reason. Oh, just to show you the summary. Right. Okay. All right. So let's move on. So keep in mind, I removed the top because what I'm going to do now is I'm going to create this bottleneck features. Okay. So the way that the bottleneck features are generated is we're going to say from the train folder, we're just going to send in all those 100 by 100 by 3 images, and we're just going to take the output. Okay, so the output. So the way that you get the output is you just go model.predict generator. Okay, so this is the key part over here. Model.predict generator will take all those 100 by 100 by 3 images and convert it into 3 by 3 by 512. Okay, so it's not, I wouldn't really call it an image anymore, it's just some sort of tensor. So again, what we did is we popped the top of the VGG16 network. Okay, and then we rescaled the images so that it's between 0 and 1. And then we're going to put it through this network. So because we pop the top, it doesn't end up as a we don't have the dense layers to end up with a like a flat layer that predicts the probabilities. It's only predicting whatever comes out of this last max pool. Okay, we don't have the dense layers anymore. So that's why I end up with a 3 by 3 by 512. Now this takes a long time. Okay, so that's why I commented this out. So I've actually saved this in a Dropbox folder, and you can download it, and it downloads it right at the top. So yeah, so don't unless it's absolutely necessary for you to check this out. Don't run this section. Okay, maybe unless you have a powerful computer. And I do the same thing for the valid one. So I use the same data generator, right? And I put the test folder through it, and I get the bottleneck features valid. Okay, so, and again, it'll still give me 3 by 3 by 512, but I think I have around 5,000 images over there, and for the train set is 19,000 something. Okay, and now those bottleneck features is what I'm going to send through my new model. Okay, so I'm going to take the output of that truncated VGG, and I'm going to send it through this. So the first thing that I need to do is I need to flatten it. Okay, the reason I flatten it is because the output of that thing was a 3 by 3 by 512, and I don't want to play with that. I want to flatten it and then send it to a dense network. So I had 256 and then a 1. Okay, so yes, this is what my new network looks like, and I have 1 million parameters. Okay. Yeah, so I did have to specify the input shape again, because the first layer, keep in mind, you have to specify input shape. So the optimizer, I use RMS prop, which is reasonably good, and then binary cross entropy is the loss. Okay, so once I start classifying on this, on that train set, so keep in mind the bottleneck features is my train set. I start getting on the train set in itself, the accuracy starts improving pretty fast. Okay, so all these epochs ran really fast on the CPU, and we get up to 92% accuracy. And even on the test set, I end up getting 92% accuracy. Okay, so we gotten off to a really good start on transfer learning. So this, you can stop here because this in itself is transfer learning, and this is good enough. But we can do better. Okay, so one way to do better is to keep training it and see how you get, but you run the risk of overfitting. The second thing that you can do is we can go back and play with one of the convolutional layers. Okay, so what we do here is, again, I'm getting the VGG16 network. Okay, so ImageNet weights, and you had to specify image, the input shape. Now the new combined model is going to say that, so keep in mind over here, I'm not using a sequential class. So this is important. I'm not using a sequential class, instead I'm using the model class. So in that one, I had to specify what the inputs are, which in this case is whatever comes through the VGG16. The outputs is going to be my model I just trained and got 92% on, but the input to that is the output of the VGG16. Okay, so really study this line and try and understand it. Okay, but this time what we're going to do is we're going not only are we going to say the dense layers are trainable, but also the last convolutional layer. Okay, so again, not only are the dense layers trainable, but the last convolutional. Everything else is not trainable. Okay, so when we look at the summary of this thing, so the first few, like the first, well, there's more than a few, convolutional networks are going to be fixed. Okay, so it's, I think, from here, yeah. So from here onwards, it's going to be trained. Like max pooling is not a weight set, so there's no parameters here, as you can see. Yeah, so over here, what's really confusing to me is that it's not really showing the dense layer network. Okay, so this is the model that we just trained. It just says that's a sequential network. Okay, so so we're training the convolutional ones, and we're going to train the weights that we just trained. Okay, so we have a bit more parameters. So over here I have 3.5 million parameters. So keep in mind there's still 15 million parameters, but they're not all of them are trainable. Okay, so there's 12 million parameters that are not trainable. Okay, it's just the last convolutional and the dense layers. Now here's the tricky part. So because we just trained the last weights, right? So we don't want to lose the gain that we just got. Okay, so because of that, because it's already trained and doing a reasonable job, what we want to do is we want to change the weights really slowly. Okay, so that's why I set the learning rate to like 10 to the power of -4. Okay, so I'm saying that it's RMS prop. Like I think in the Keras block they just use stochastic gradient descent. I think might have done better, but anyway, so the main point is you need to set the learning rate to be 10 to the like a small number, just because you've already got a trained model, and if you move too fast, you're just going to lose all the progress that you just made. Okay, so because in general, when you generate a network, in the first few steps, it's going to take large steps, and later on, it's going to slow down. Okay, because we've already trained it, we need to make sure that it understands it needs to take small steps. Okay, so that's what it's doing over here. And then we say metrics is accuracy, and then train as usual. Now, so let me just show you the results. So, so in this case, like I say, the data generator is so there's zoom range and a shear range and the horizontal flip, right? And one stupid thing that I didn't do before is create a test data generator. Okay, so and the test data generator is simply rescaling it to be between 1 and 255. I don't necessarily want to try and do these fancy things that I've done. You can, I suppose, because it's an image, it doesn't really hurt. But yeah, I'm just going to rescale it. So it's different. The trained data generator and the test data generator is different. Now, I got a bit sidetracked there. So coming back to what I was talking about before. So to show you the results of the training, unfortunately, it actually gets worse in this case. So it starts off with being 91% and then gets worse. So I think even the 1 to the -4 was a bit too much. But again, just notice how long it took. Okay, so it was a bit less than an hour for me to run through the epoch. And the reason for that is this time I'm actually running it through all those 15 million parameters. Okay, so each image needs to run through 15 million parameters to get to this point. And so in my opinion, that's why it's not doing a great job as I would have. Well, it's doing a slow job of whatever it's doing. So on a GPU, this would have gone through really fast because that's what GPUs are best for, parallel computation. So that's transfer learning for you. Maybe next time I will show you how to get a GPU instance on Floyd Hub. But yeah, so we're going to stop it. Oh, actually, I almost forgot the most important part. So I just went ahead and did some predictions on images that weren't in the original images, like the Doge meme. It's not in the original thing. One thing that really got me was I forgot to divide the input image by 255. Okay, so that was a gotcha that I didn't really realize until much later on, and it just kept classifying everything as cats. Okay, so remember to divide whatever you get by 255. So it's the same distribution as the original data that you had. So once I did this, the Doge meme, so it's saying it's 67% probability that it's a dog. Grumpy cat, it's a tiny percentage that it's a dog, so it's obviously a cat. Trump cat, so it's 20% cat, 20% dog. Sorry, so okay, so it's correctly classified it. And this one again, it's 32% chance that's a dog, so cat it is. And one thing, and if you really do care, I did this as well, right? So so the probability that this is a dog is 99%, 99.99%. Okay. Okay, so that's it for my lesson. If you have any questions or comments, please do let me know. Also, please subscribe and star my repository on deepschool.io. And thanks for watching.